And at long last, we finally begin some of my favorite mathematics, stuff I've been talking about all year, logarithms. This concept, like I said, can be very abstract for students. I'm going to need you to ask me questions when you have them. Don't think, I'll get it eventually. Please don't. I need you to ask me questions. Please. If you have any questions at all, you ask them. It's too important not to. Definition of logarithm with base b. Notice b for base, as usual, b for base. So let's say that b, base, and y are positive real numbers, and the same rule applies that we were talking about with exponential growth and decay. Base can't be 1. The logarithm of y with base b is written like this. So we say log base b of y. That's how you would say that, log base b of y. Log base b of y equals x if and only if b to the x equals y. If and only if means it's true this way and that way. So what does all that mean to you? I will explain in a moment. So let's get to some math that we can all just do in our head, right? I'm telling you 2 to some power is 4. What is that power? 2 to what power would give me a 4? A 2, yeah, that's obvious. And how about over here? 2 to some power is 8. What does that power have to be? It has to be a 3, right? Now, those were easy because those were powers of 2 that you know. But is it okay to just say, well, I just know that's the answer because it is? I mean, isn't everything in math about operations? We add, we subtract, we multiply, we divide, we raise powers, we root things. We don't just say, I know that's the answer because it is the answer. That doesn't make any sense. So you're looking at these and you're going, yeah, I know the answers. But if I said to you, show your work, how did you get that answer? You'd be stumped. Look at this. 2 to some power is 6. Now clearly 4 and 8 are perfect powers of 2 and 6 is not. And well, if this was 2 and this is 3, since 6 is between 4 and 8, you expect this answer to be between 2 and 3. And it is between 2 and 3, but you know what it's not? It's not 2.5. I know you wish it was. I wish it was, but it's not. How do we know it's not 2.5? Because, remember, the half power means square root. So if you said 2 to the 2.5, you're actually saying 4 root 2, which does not equal 6. So then how do you figure out what this power is? The answer is logarithms. Would you like to know what this exponent is? I know what this exponent is. 2 raised to the, right of this, log base 2 of 6 equals 6. That is the unknown exponent. And yet, I still haven't told you really what's happening, have I? You still have no idea what a logarithm is or what a logarithm does. Let me show you the way that a lot of Algebra 2 teachers teach this stuff. They say, okay, this is logarithmic form of a true statement. And I recognize it as logarithmic form because it has a log in it. Does that make sense? So I say, oh, log base b of y equals x. This is the exact same thing as saying b to the x equals y. And this is exponential. And what they do is they say, here's how you convert from one to the other. Now I'm going to show you this because it's a trick that works, but it does not explain to you what a logarithm is. And that's why you'll never see me do it again after this. A lot of Algebra 2 teachers go, look, if you want to transform this log statement into this exponential statement, all you have to do is draw this arrow and say b raised to the x equals y, which is what that says right there. And they tell you, oh, that's how you move between log form and exponential form. And if you wanted to go from this exponential form to this log form, you would say log base b of y equals x. And you go, oh, look, that's how you go between the two forms. But you still don't know what that means, do you? And that's why I will never ever show you that again. Because as far as I'm concerned, that's magic. That's not algebra. I'm going to teach you how to do these things using algebra, and they will make perfect sense. Yes, Nick?
So what is that arrow supposed to mean?
This arrow is the trick that a lot of teachers teach their students how to use to move between an exponential statement and a logarithmic statement. And still, that makes no sense, does it? Let me grab a piece of scrap paper real quick and show you something. This is lined paper, but it'll work. Let me write a true statement. 2 raised to the 3 equals 8. Absolutely true statement, right? Okay. This true statement can be written in two different ways. This is the exponential way of writing this absolutely true statement. The logarithmic way of writing this absolutely true statement is log base 2 of 8 equals 3. These two statements say exactly the same information. They just say it in different ways. For example, 1 plus 2 equals 3. Absolutely true statement, right? But isn't it also true that 1 equals 3 minus 2? All I did was subtract this 2 from both sides. These two statements say the same thing. One of them uses addition to show you the true statement. The other uses the inverse of addition to show you the same true statement. That's what logarithms are. Logarithms are an inverse operation. The word log does not have value. The word log is, unfortunately, a symbol, like a square root bar or a plus sign. It is a symbol. Every log has a base, kind of like how every radical has an index, right? There's square roots, third roots, fourth roots, fifth roots. Every log has a base, just like how every radical has an index. So a third root is an operation. A fifth root is an operation. A log base 2 is an operation. A log base 5 is an operation. Everything in math that can be done can be undone with an inverse operation. Logarithms are an inverse operation. Their job is to cancel this base. A couple days ago, Lewis asked me, I don't know if you guys were paying attention when he asked if we were going to have a way to solve for unknown exponents. And I said, yes, we will. Ta-da! Logarithms. That's how you solve for unknown exponents. I mean, if I gave you this statement, x raised to the third equals 27. Let's not say 27. Let's say, I'm trying to stay away from 27 because it's a lot of threes. Let's say 64, okay? You have a way of solving for this unknown base, don't you? You would use the inverse operation of a third power, right? You would use a third root. Notice how the index and the exponent match, right? And this is how you cancel that, because they're inverse operations, correct? Imagine for a moment, and I'm about to draw some symbols that are made up. They are not real math symbols, but I think they are really going to help you to understand what the logarithm is doing. Allow me to write this different. Let me say, instead of saying x to the third equals 64, instead I'm going to say 3 to the x equals, I don't know, 81. Now you might know what the answer is. You might know that the answer is 4. But that's not good enough. What operation allowed you to write x equals 4? There must have been an operation. There must have been a way to get this alone. That means there must have been a way to make that go away. Yes, Nick?
Couldn't you just like take 81 as like you know that you're gonna be no matter like how many times you keep multiplying by 3, you're gonna have to like multiply by 3 on like the last number to get 81. So can't you just keep on dividing by 3 and count how many times it takes until you get to 3?
So you're asking, since I know that this is a power of 3, couldn't I just see how many times I had to divide it by 3?
Yes.
That only works if that number is a power of 3.
Alright.
But as you can see, there is no way to do that, is there? Because 6 is not a power of 2. If it's perfect like these two, then yeah, that would work. But logarithms are actually useful when it's not perfect. I'm just using one that is perfect because I know that you trust this answer, right? So what is the operation that makes this base 3 go away? I'm about to draw a symbol that is not real math. I'm just helping you understand what a logarithm does. You're comfortable with this root type canceling this exponent, right? That's comfortable for you because they match? Just take this trip with me for a moment, okay? What I've just drawn, does it make sense that it would do that? I mean, this root type canceled this exponent, right? So why couldn't there be, let's call it a base root type that cancels a base? Doesn't it make sense that something like that should exist for mathematics? Doesn't that make sense? Well, it does. It's just that that's not the symbol we use. I made that symbol up. Instead of this symbol, we use log base 3 to cancel exponential base 3. So let me start over again. And don't worry, we will get to the actual notes in a moment. Notice the space I've left. If I want to cancel an exponential base 3, I must use a log base 3 on both sides. That is the operation that cancels exponential base 3. You see how the bases match? You see how the exponent and index match? They have to match. And what happens is this x falls down out of the sky, and you get that x equals log base 3 of 81, which, by the way, is 4 because, 3 to the 4th is 81. But that is what a logarithm does. It cancels a base to leave an exponent alone. Yes, Nick?
So multiplying log base 3 like anything like
I'm not multiplying. It's an operation. It's like square rooting. I'm taking the log base 3 of something.
like the log base 3 cancels out that 3.
Exponential base 3, because they're inverses. It's like plus cancels minus.
Alright, yeah, and then the x falls down, and then like, how do you get the 4 from looking at that log base 3?
Because you know that 3 to the 4th is 81.
Alright.
But that is a perfect thing, and that's just how we represent. This is how we represent canceling exponential base 3. It's the best thing mathematicians could come up with. I think this is better, but I made it up, so we can't use it. It'll make more sense as we work with them, okay? So just now that you have seen what they are and what they do, let's work with these things now.
So you just use it to find out like what power you need to raise, whatever your like log number was to get
The base, yes.
number that you were talking about.
It's called a base because it's representing, well, what if it was the exponential base? And your answer is the exponent. Yeah. So here I have 4 statements that are written in exponential form. 1, 2, 3, 4, A, B, C, D. We're going to write them, these are written in logarithmic form because there's logs in them. We're going to write them in exponential form. And I'm not going to use this cutesy little trick. I hate this trick. This is magic. No. We are going to use algebra. Now, class, it's time for me to teach you a script. When I prompt you with certain questions, I need you to answer me as a class. Now, I know that my Algebra 2 students do not like to speak to me for some reason. I don't know. But I need you to answer me as a class. It's like a chorus situation, right? Right? A chorus situation, and there is a reason why. Please trust me on this. If you play this game the way I want you to, you will be amazing. When I say something like, okay, class, that's your indicator. He's expecting us all to answer together. And I would ask a question like, okay, class, how do I cancel a log base 2? Now, the response I'm looking for is for my class to say exponential base 2. Basically, it works like this. If I say what cancels log base, you say exponential base. And then whatever number I said, you say the same number. If I say, okay, class, what cancels exponential base? You would say logarithmic base. And then whatever number I said, you say the same number. You see, because the log base has to match the exponential base. The exponential base has to match the log base. And as long as the bases match, they cancel. So we'll try. I say, okay, class, what cancels log base 2? You would say exponential base 2. Now let me show you what that looks like. When you say exponential base 2, what you're telling me is to perform an operation on both sides of this equal sign. You're telling me to pretend there was a big exponential base 2 on both sides. So it actually said 2 raised to the log base 2 of 16 equals 2 raised to the 4. That's what you're telling me to do. It's like telling me to take the square root of both sides, only it's a log. On the left side, exponential base 2 will cancel log base 2, and what you're left with is the exponential statement 16 equals 2 to the 4th. You haven't solved for anything. You haven't evaluated anything. You took one true statement, rearranged it into a different kind of true statement, much like I did right there at the top, where 1 plus 2 was 3, but also 1 is 3 minus 2, where you use an inverse operation to rearrange the information, but it still says the same thing, just in different formats. Does that make sense, what I'm saying? Let's turn this exponential statement into the exact same information, only written in log format. I don't like magic. I like algebra. So what I want to know is what operation will get this thing into logarithmic form. Well, I ask myself, what do logs do? They cancel exponential bases. So I say, okay, class, how do I cancel exponential base 5? You would say log base 5. You just told me to take the log base 5 of both sides of this equation. Now, I don't have the space to write it here like I did that, so I'm going to write it off to the side. You told me to take my 5 to the 2 and take the log base 5 of that. The other side was a 25, and you told me to take the log base 5 of that as well. You told me to do something to both sides of the equation. And log base 5 is an operation that would be performed on two sides of an equation. On the left side, log base 5 will cancel exponential base 5. And you're left with the 100% exact same statement, but instead of exponential form, it is written in logarithmic form. Now, the parentheses are only necessary when there's a lot of other crap going on. As you can see, I didn't use parentheses on any of these logs here. But the reason why I did it here was because I wanted you to understand that I was capturing the entire side of the equation. Much like I was doing when we were doing transformations at the beginning of the year, I'm doing this to both sides of the equation. Before we go on to more things, do you have any questions about the concept of log or what I'm doing or why I'm doing it or anything like that? It seems easy, doesn't it? You know why? Because it's algebra. It's not magic. And you could go ask any other Algebra 2 students on this campus. You could go to SCF when you dual enroll and things like that, and you can ask most of those students what they think about logarithms. And they'll tell you they hated them and they're difficult. You know why? Because their teachers taught them like they were freaking magic. They showed them these things and said, don't worry about what it means or why it's true, just do it. No. There is no magic. There's only algebra. Things that undo each other in mathematics. So on the left side, it says log base 4 of 1 is 0, and this is absolutely true. I want to take this absolutely true logarithmic statement and write it in the same absolutely true exponential form. So I'd say, okay, class, that means I need this log base 4 to go away. What cancels log base 4? And my class would say exponential base 4. What you're telling me to do is pretend that these two things are actually exponents and that their base was 4. So this thing actually said 4 raised to the log base 4 of 1 equals 4 to the 0. Exponential base 4 and log base 4 cancel each other out. And it leaves this absolutely true statement, 1 equals 4 to the 0. Yes, Nick?
So do you cancel out that log base 4 by just multiplying by exponential base 4?
I didn't multiply, I used the exponential base 4. What I did was I pretended both sides of this equation were actually exponents. And the base that wasn't written was 4. Why wasn't it written? Because it was the same on both sides, so we didn't have to think about it. But if you do write it, you can see these two operations cancel each other, like plus and minus, or square and square root, or multiply and divide. So I'm not multiplying anything, I'm not dividing anything, I'm using an inverse operation. I'm exponential base 4ing, what a weird thing to say, both sides of the equation. Now this has an arrow pointing at it to you. It says that this is a special log. The reason why this is a special log is because this base didn't matter. Because when I wrote it in exponential form, it was going to be that base raised to the 0, right? This could have been a base 5, a base 6, a base 7, a base 20, a base 38. It wouldn't have mattered because over here it would have said that number raised to the 0. And everything raised to the 0 is 1. So the special log says this: log base b of 1 is always 0. Base b means I don't care what number you put there, your answer, your evaluation will be 0. But remember, the base is not allowed to equal 1, which is what it says at the very top of the notes. And it also says that it must be positive. So we're talking about a number that must be bigger than 0 but can't equal 1. Sounds oddly familiar, doesn't it? Almost like it was the exact same rules for the exponential bases. Remember, must be positive, couldn't equal 1. That's because they're inverse operations. They have to follow the same rules. So that's a special logarithm. Now over here, there's nothing special going on here, and that's why it doesn't have any arrows pointing at it. But I would like you to see negative exponent. Now you guys can tell me, what does a negative exponent do to a number or an object of any kind? Right, it puts it on the other side of its own fraction bar. So this is a true statement because this equals 1 over 10. This is 1/10. But I want to take this exponential statement and put it in log format. That means I need to cancel exponential base 10. So I say, okay, class, how do I cancel exponential base 10? My class would say log base 10. So I'm going to take the log base 10 of both sides. In here I had a 10 to the negative 1. Over here I had a 0.1. The log base 10 and exponential base 10 will cancel each other out, leaving behind the true statement that negative 1 does in fact equal log base 10 of 0.1. Now I can't quite remember where this is going to come up. Oh, okay, it's going to come up later in the notes. All right, I don't need to say it yet. I found it. Comfortable? Calm, cool, collected? I hope it doesn't look like magic. I hope it looks like I'm just doing the opposite operation on both sides of an equation, because that's all I'm doing. It's just that you've never seen this operation before. It's unfortunate that it's a word, isn't it? I wish it was just some shape. I wish it was just a root radical of some sort, like a base root or something like that. Yeah?
So what is it exactly that makes the log base 10 cancel out that 10?
The exponential base 10?
Yeah.
They just are inverse operations. That's why I have to say log base. What I'm saying is I need a way of canceling exponential base. So I'm using a log base. It's like I said, the reason why this seems weird to you is because it's the word logarithm. But it would be like me writing the word root instead of drawing the square root. Does that make sense?
Yeah.
Because that's all it is. It's just an operation. But unfortunately, mathematicians never gave it its own symbol. I don't know why. I don't know why we don't use my inverted radical. I can't explain it. Because that's exactly what it's doing. I mean, you show this to people, and then you show this to people, and they go, well, yeah, that makes perfect sense. I don't know why we don't use that symbol. I'm going to be honest. Yes, sir. No, I just wrote those parentheses out of habit. Now, again, the parentheses are just there in case there's extra stuff. How about I stop saying stuff? Let's use academic vocabulary. The information that is inside the parentheses, or I'd like to say is inside the logarithm, is called the argument. It's called the argument of the logarithm. And that's academic vocabulary that will carry forward into trigonometry and everything. When you start having insides of operations, like inside sine, inside log, inside, what else do we have that have arguments? Oh man, there's all kinds of stuff, like the greatest, what is it, the floor function, things like that. There are, when you have to have an quote unquote inside of parentheses information, we just call it the argument. So when the argument has a lot of things going on, like plus and stuff, like x plus 3, you need to wrap it all in those parentheses. Otherwise, the plus 3 is working on the outside of the logarithm instead of the inside. It basically changes the kind of transformation that it is. That's why we need the parentheses. Now, log base 10 of 0.1, I just wrote the parentheses out of habit. There or not, doesn't matter. This is an absolutely true statement. I would like for you to see that this says log base 12 of 12. If I had just written Can I cover that up? Does that work? Boop. If I had just written that, how do I want to say this? If I had just written 12, there we go, and I asked you, does this 12 have an exponent? You could have said yes. What would that power have been? A 1, right? I mean, we don't have to write that, but every number does have a power of 1 up above it, right? So couldn't I just say that there was a power of 1 right here? And then say, class, what does log base 12 cancel? You would say, oh, look, right? That's why that's a true statement. Okay, but I shouldn't have done that in pen. I should have done it in pencil. I'm sorry. Don't cross that off with pen like I did. Now I'm going to have to rewrite the question. I was just explaining to you why it was true, because I wanted to jump ahead to the special log. But let me rewrite it and have us walk through the process that I asked you to do with me. I go, all right, I'm trying to get this out of log format. I'm trying to get it in exponential format. That means I need to cancel my log base 12. And I say, okay, class, how do I cancel log base 12? You would say, what? Where's my class? Lots of voices. I'm telling you guys, I'm telling you this is the way to go. If I say, how do you cancel log base 12? You would say? Exponential base 12. There you go. Thank you, good little robots. Exponential base 12 on both sides. There's someone in the waiting room. She's early. She's in my third period. Yeah, they don't pay attention. And what is going to go on here is this. Whee! So there we go. 12 equals 12 to the 1, which is absolutely true. 12 equals 12 to the 1. So what is going on with the special log? What was special about it? Well, what was special about it was that the argument and the base of the logarithm matched. So when you have log base b of b, meaning if the base and the argument are equal, this logarithm has a value of 1. Why? Because anything to the first power equals itself. That's why. Now, I'm clearly not going to finish these notes today, and that's okay. It's not a big deal. All right? Let's take this true statement and write it in log format. By the way, why does 8 to the 2/3 equal 4? This is last chapter. This means third root of 8, right? Third root of 8 is 2, and then you square it, and you do get this 4. So that's a review of last chapter stuff. Let's take it out of exponent form. Let's get it in log format. And I say, all right, class, how do I cancel exponential base 8? You would say log base 8 of both sides. So we would take the log base 8 of both sides of the equation. Over here I have an 8 to the 2/3. Over here I have a 4. And yeah, log base 8 does cancel exponential base 8, allowing that power of 2/3 to drop down from the sky. And it says 2/3 does equal log base 8 of 4. Of course it does. Oh, this is the first logarithm that has a negative value. Gee, I wonder why I had a negative value. What makes this one different from all the other ones you've seen so far? Huh? Yeah, but why? Why do you think it's negative? What about this statement is different from the other logarithms that I've showed you? Ah, there's a fraction in the base. Basically, when one of the numbers is a fraction and the other one isn't, your logarithm will have a negative value. That's basically how that works. But anyway, I say, all right, class, I need to get it out of log format. What cancels log base 1/4? You would say? Exponential base 1/4 on both sides then. So we base 1/4 both sides. The exponential base 1/4 and log base 1/4 will cancel and leave behind the same true statement in a different format. 4 equals 1 over 4. And I am going to write this in parentheses. That way it doesn't look like only the 1 has the power of -1. Ta-da. I mean, yeah, look, when you raise a fraction or a negative exponent, the whole fraction flips over. Ta-da! It is true. And then over here, I think it's kind of obvious what's going to happen. I'm going to have to cancel this exponential base 6. All right, class, what cancels exponential base 6?
Log base 6.
Log base 6 cancels exponential base 6 on both sides. I have more space. So log base 6 of that side and log base 6 of this side. I have a 6 to the -3 here, and I have a 1 over 216 there. And yeah, deuces. -3 does equal log base 6 of 1 over 216. Why did I write that in parentheses? Just because I didn't want this base to look like it was part of the bottom of the fraction. It's the only reason why I bothered. So look, when one's a fraction and the other's not, again, negative value. And I think that that's a good place to call the beginnings of logarithms for today.